Metal casting is an intensely violent physical process. Extreme heat and rapid phase changes are required to turn raw elements into heavy machinery. This process is essential because it allows manufacturers to create the dense, solid geometries required by high-performance sectors, like the heavy engine blocks that drive the automotive industry. The aerospace industry relies on this exact methodology to form massive structural components and jet engine parts, where physical integrity is an absolute requirement. But the thermodynamic violence of casting inevitably causes problems. As molten metal cools, it frequently traps expanding gases or solidifies unevenly, creating microscopic empty voids suspended inside the metal. A surface-level quality inspection of these parts reveals absolutely nothing. The component appears mathematically perfect and solid from the outside. If a hidden internal void remains undetected in a high-stress component, it will eventually cause catastrophic mechanical failure under load, snapping the part entirely. Preventing these industrial disasters requires a method to see inside solid metal without destroying the component itself. This is the definition of non-destructive testing, or NDT. To evaluate the internal volume of casted metals, X-ray testing serves as the primary industrial standard. While the underlying mechanics are similar to medical imaging, industrial X-rays require massive amounts of energy. Penetrating inches of dense steel or titanium requires an energy output far beyond what is used to scan soft human tissue. The output of this high-energy process is a radiograph. A radiograph is a two-dimensional map of the object's internal architecture. This shadow map provides exact coordinates and sizes for any internal anomaly, allowing engineers to find the flaw before the part is ever installed in a machine. Industrial X-ray NDT translates the physical density of an entirely opaque object into readable, actionable data. This diagram shows the core scientific principle governing this technology: differential attenuation. Differential attenuation is the rule that as energy passes through a material, its intensity drops based on the material's physical properties. As high-energy photons pass through the metal, their intensity drops inversely proportional to the material's thickness and density. High-density areas absorb the radiation. On the final image, this lack of passing photons registers as a light or white area. However, when those photons hit an internal void or a pocket of trapped air, the physical resistance drops. The radiation passes straight through this empty space at near full strength, burning a dark black spot onto the radiograph. A trained inspector reads this resulting gradient of black, gray, and white to reverse engineer the internal three-dimensional structure of the part. Every dark spot on a radiograph is a literal map of missing mass, representing a structural weak point. Capturing an accurate image requires strict preparation. Technicians must first clean the casted part, removing any external dirt or oxides that could cast false shadows. Next, they ensure perfect geometric positioning. The part must be aligned precisely between the X-ray tube and the detector to prevent the image from distorting. Technicians then calibrate the exposure parameters based directly on the specific alloy and the thickness of the metal being tested. They adjust the voltage, or kilovolts, to dictate the raw penetration power of the beam, and they tune the current, or milliamps, to control the contrast and detail of the image. An improperly calibrated machine will either completely blow out the image with too much energy or fail to penetrate the metal entirely, rendering testing useless. Once the radiograph is captured, the inspector translates the abstract dark shapes into specific manufacturing failures. This diagram outlines the 5 primary casting defects, starting with gas-related flaws. Gas porosity occurs when tiny pockets of gas become trapped in the cooling metal. On a radiograph, these appear as small, perfectly circular, smooth, dark dots. When severe venting failures occur during casting, massive localized gas pockets form. These are known as blowholes, and they register as large, prominent dark voids. The next major category covers thermodynamic defects, specifically shrinkage cavities. As molten metal solidifies, it physically contracts. If it lacks enough liquid material to feed that contraction, the metal pulls apart internally. This creates jagged, branching dark shapes, visually distinct from smooth gas bubbles. Then we have the most dangerous defect, cracks. Cracks are stress fractures caused by uneven thermal contraction across complex geometries. The metal snaps under its own internal tension, leaving fine, dark, sharp linear lines on the radiograph. And the final primary category is inclusions. Inclusions are pieces of foreign material, like sand from the mold or stray slag, that become permanently trapped inside the solid metal. Inclusions are unique in radiography. They can appear either darker or lighter than the base metal, depending entirely on whether the trapped debris is denser or lighter than the surrounding alloy. By memorizing these morphological signatures, an inspector can look at a set of shadows and determine exactly what went wrong on the factory floor. While highly effective, this diagnostic power introduces severe biological risks to the operators. The massive energy required to shoot through thick steel acts as ionizing radiation to the human body, capable of damaging tissue at the cellular level. Because of this, testing requires specialized heavy lead-lined bunkers designed to contain the scatter radiation. Operators maintain strict time and distance protocols, set up controlled area barriers, and wear mandatory dosimeter badges. Dosimeter badges are personal tracking devices that measure a worker's cumulative daily radiation exposure. The logistical footprint required to safely manage radiation exposure adds significant complexity and cost to the testing process. Historically, X-ray NDT was limited by its reliance on traditional chemical film, which was slow to process and physically degraded over time. Modern facilities now utilize computed radiography and digital radiography, replacing chemical film with reusable imaging plates that capture instant, high-resolution data. The bleeding edge of the industry is 3D computed tomography, or CT scanning. It captures hundreds of angles to build a fully volumetric model. This eliminates the issue of overlapping shadows and allows artificial intelligence systems to automate defect detection with near-perfect accuracy. Regardless of the technology utilized, all results are governed by strict international acceptance criteria set by organizations like ASTM, ASME, and ISO, global engineering bodies that standardize manufacturing safety. These standards dictate the exact mathematical tolerances required to pass inspection, deciding exactly how large a defect must be before a $1 million turbine component is scrapped. Industrial X-ray NDT functions as a vital data gathering system. By consistently identifying internal flaws, it optimizes the global casting industry and guarantees the structural integrity of our most critical infrastructure.